Welcome back, students. Today we are going to continue with the part 3 of numerical problems from chapter 5, work, energy, and power. Okay, so this is the exercise problem 5.13. So the problem statement is as follows: a raindrop of radius 2 millimeter falls from a height of 500-meter above the ground. It falls with a decreasing acceleration due to viscous force of air until at half of its original height it attains a maximum terminal velocity, okay, terminal speed. So a water drop, it is falling from an height, okay, so there is air in between the earth surface. So this is a water drop and this is the earth surface. We have air all over. Okay, so this water drop is traveling through this air. Okay, so as it if it there is no air, the waterfalls constantly accelerate and its velocity increases. But due to this air resistance, there is a friction between the water drop and the air. Okay, so that frictional force is directly proportional to velocity. Okay, so as a result, as its velocity increases, the frictional force also increases. So at certain point, the velocity of the water drops attains a uh, saturation velocity, okay, maximum terminal velocity. After that, the velocity won't increases, okay. So such kind of velocity is called the terminal velocity. After that, the water drops fall at a constant velocity. Okay, so this is the idea to solve the problem. They have also provided the constant velocity, which is 10 meters per second. Okay, so they asked to find work done by the gravitational force on the drop for till up first drop, so till this distance, and after that we have to calculate another work done in the second half. Okay, so the total height is 500 meters. So this is the input they have given. So we have to solve for first 250 meters and the second 250 meters. What is the work done by the resistive force in the entire journey if its speed on reaching the ground is 10 meters per second? They also asked the work done by the viscous force of the air on this water droplet. Okay, so let's start the problem. So before going into the problem, we need to have certain values. So we assume the density of water. It is not an assumption, but the water density slightly changes. But in this problem, we consider the water density as 1000 kg per meter cube. Okay, so this is the density of water. So let me write it as rho equal to 1000 kg per meter cube. That is one meter cube of water weighs 1 ton. Okay, that's the idea of density. So the next thing is we need acceleration due to gravity. Here we are assuming the value of 9.8 meters per second square. No, this is also not assumption. This is the value of acceleration due to gravity. Okay, due to the earth. So let's calculate the mass because we are interested to find the work done. Okay, for that we need mass. So in order to find the work done, we will find the work done either through change in kinetic energy or from the potential energy. Okay. So for both the cases, we need what's called the mass because for kinetic energy, the formula is of mv square, and for potential energy, the formula is mgh, where h is the height we are considering. Okay. So So in order to solve both these quantities, we need mass. Okay, but we nowhere have the value for mass. They have provided the radius of the raindrop, and from these quantities we can find the mass of the water drop. Okay, so calculation of raindrop mass. Yum. Okay. So we can first we have to convert the radius to meters. Therefore, R they provided us 2 millimeter. Okay, which is 2 into 10 power minus 3 meters. Okay. Next, we want to find the volume. Okay, volume of the raindrop. So V equal to, if we assume the shape of the raindrop as a sphere, then we can have the volume as 4 by 3 pi r cube. Okay, from this we can find 4 by 3 into 22 by 7 or 3.14, whatever you want to use, you can use. So let me use as 22 by 7 into 2 into 10 power minus 3 whole cube. Okay, this value r cube. So I have calculated this value already, and this value is approximately 33.51 into 10 power minus 9. This comes from here. Okay, so next we want to find the mass. Okay, mass of the raindrop. So we know that density equal to mass by volume. Okay. So we know the density and we also know the volume. From that we can find the mass. Therefore, mass equal to rho times volume. This is not velocity. This is volume. Okay. Which is, we know it's 1,000 kg, and we have to multiply by the volume 33.51 into 10 power minus 9. Okay, so this is 10 power 3 and 10 power minus 9 will be, we can write the mass as m equal to 33.5. Let me drop this one into 10 power minus 6, or we can write it as 3.35 into 10 power 5. Okay. So we have the mass now. We can calculate the work done by the gravitational force on the raindrop. Okay. So work done by the gravitational force is nothing but equal to m into g into h. Okay. So here they have asked us to find the work done till first half, and also for the second half. Okay. So let me break the total distance into two parts. One is 250 kilometers. This is the first part, and the second part is another 250. Okay. So total height, total height h equal to 500 meters. This is the total height. Height of first of h1, let it be h1, which is 250 meters. Therefore the height of second of h2 will be another 250 meters. Okay, so work done for the first half, we are calculating work done for the First of, let me name it as WG1. Okay, so WG1 equal to MGH1, this distance, which is equal to, we have 3.35 into 10 power minus 5 into, for G we have 9.8 into H1 is 250 meters. Okay, so everything is in the standard unit, so no problem, we can straight away calculate this. So I have made the calculation and it's approximately equal to 8.2075 into 10 power minus 2. Okay, since this is work done, the unit is obviously in joules, WG1. So since the both heights are same, so for the second hours also we will have the same value. Okay, so work done for by the gravitational force for the second of, okay, that is WG2. So WG2 is also approximately 8.207 into 10 power minus 2 joules. Okay. So we have calculated the first part of the problem. The second part of the problem is they asked what is the work done by the resistive force in the entire journey. Okay. So now we have to consider the full light. Okay. If its speed on reaching the ground is 10 meters per second. So these are the inputs they have given. So we have to calculate the work done by work energy theorem. The work done is equal to the change in kinetic energy, the net work done. Change in kinetic energy. Okay. So let me put W net equal to del K. Okay. Here W net is the work done by the gravitational force and plus the work done against the resistive force. Okay, so let me be WG be the work done by the gravitational force and WR be the work done against the resistive force. Okay, so this work done can be found by and also we have this net work done is equal to change in kinetic energy. So change in kinetic energy is kinetic energy final minus kinetic energy initial. So if we put both of these values in the work energy theorem, we have Kf minus Ki, this is from the change in kinetic energy, is equal to the net work done. Okay, so work done by the gravitational force and work done by the resistive force. They are asking to find the work done by the resistive force. Okay, so work done by the resistive force is nothing but Kf minus Ki. If we bring this to this side, we will have Wg. Okay, work done by the gravitational force, this we have already calculated. And so we have to calculate the kinetic energy, final kinetic energy and initial kinetic energy. So let's proceed with finding the initial and final kinetic energy. Okay, so initially the drop is at rest. Okay, therefore initially the velocity u of the raindrop is 0. Okay, u equal to 0, therefore initial kinetic energy equal to of m u square, which is equal to 0. Okay, so for and the final kinetic energy or the final velocity while reaching the ground is v equal to 10 meters per second. They have already provided. Okay, the final velocity p equal to 10 meters per second. Okay, so therefore the final velocity kf equal to half m v square, which is equal to 1 by 2 into 3.35 into 10 power minus 5 into v square is 10 square. Okay, so or we can write it as half into 3.35 into 10 power minus 5 into 10 power 2. Okay, so this value is half of this value is 1.675 into 10 power, this is minus 3. So this is the final kinetic energy. Okay, so we have final kinetic energy, and we need to find the work done for the entire journey. Okay, so work done by the gravitational force for the entire journey, that is 500 meters. Okay, either you can calculate wg from this equation, okay, or you can calculate from the previous value we have already worked at. Wg equal to Wg1 plus Wg2. This is the total work done, okay, by the entire drop for entire journey. And therefore this value is Wg equal to, so we have already calculated this value, and we know that the value of Wg1 is 8.2. Let me round off with 8.21 into 10 power minus 2. This is also the same value. Okay, so let me 8.21 into 10 power minus 2. Okay, so this value comes from, we have already worked that, we worked it out, this one. Okay, from this. So instead of 8.2075, I'll round off with, since this value is greater than 5, we can raise the previous value by 1. Okay, therefore it becomes 8.21 into 10 power minus 2. Okay, so this value. So this value, if we add, we get is Wg equal to 1.642 into 10 power minus 1. Okay. Or we can rewrite it as 164.2 into 10 power minus 3. Okay, so what I did is I divide by 100 and multiplied by 100. Okay, so I think this is straightforward. For those who can't understand, and just do it. So if you multiply this number by 100, then you have 1. So this point moves two values. Okay, therefore 164.2, we have 100 down. Okay, so this 100 into 10 power minus 1. Okay, so this is actually 164.2 by 10 power 2 into 10 power minus 1. Okay, so if you bring this here, then it will become 164.2 into 10 power minus 1 into 10 power minus 2. Okay, if this comes to the numerator, it will become 10 power minus 2. So since the base are same, we can add the value. Therefore we get 164.2 into 10 power minus 3. Okay, so I think this thing everyone knows. For those who can't get this, so I am explaining for that people. Okay, only one time. So we can write Wg as 164.2 into 10 power minus 3. Okay. So let's calculate the resistive work done by the resistive force. Work done by the resistive force. So we have already made the formula for all this. The work done by the resistive force is this. Okay. So we now know the final kinetic energy, initial kinetic energy, and work done by the gravitational for the entire journey. So work done by the resistive force. This Kf is, we found that as 1.675 into 10 power minus 3. 10 power minus 3. And for k initial it's 0. Okay, so we have already worked it out. This k initial is 0. K final is 1.675 into 10 power minus 3. And also we work for Wg minus Wg is work done by the gravitational force for the entire journey, 164.2 into 10 power minus 3. This is the reason I convert this value from 10 power minus 1 to 10 power minus 3. Okay, because both these value are same powers of 10, therefore it is easy to do the arithmetics. So we can take 10 power minus 3 outside, so we end up with 1.675 minus 164.2 whole into 10 power minus 3. So I have already worked this out. So the value is 0.163. Okay, we have to multiply 10 power minus 3. So actually it is approximately 163 point 163.0 into 10 power minus 3. So if we multiply, it will be 0.163. Okay, joules. Since this is the work done, so the unit is obviously joules. So this is the work done by the resistive force. Okay, so this resistive force acts in the opposite in the direction of displacement. Okay, so if we consider the raindrop displays in this direction, but the resistive force acts in the opposite direction. So the angle between them is 180-degree, and we know that whenever the angle between the force and the displacement is 180-degree, we have negative. Okay, because we can also find the work done as F into D into cos theta. Okay, mod F vector mod D vector cos theta. When theta equal to 180-degree, cos 180 is minus 1, therefore we get a negative value. Okay, so this is the idea. So this is the problem they asked to solve, and we have solved it. Okay, so the negative sign implies the work done by the resistive force is against the displacement. It's opposite in the direction of displacement. Okay, so let's move on to the next problem, so which is 5.15. Okay, I skipped the exercise 5.14 because there is a reason. So this problem and the problem which I have discussed earlier have some similarities in the calculation. So I grouped these problems together. Okay. So that's the reason. I'll explain that problem 5.14 afterwards. Okay. So let's start with this problem. This is exercise 5.15. The problem statement is as follows: a pump on the ground floor of a building can pump a water to fill a tank of volume 30 meter cube in 15 minutes. Okay, so if the tank is 40 meters above the ground, the efficiency of the pump is 30%. How much electric power is consumed by the pump? So this is the problem. So we have a overhead tank, and this is the ground level. So this tank is at 40 meters from the ground level. It is at 40 meters from the ground level, and the volume of the tank is 30 meter cube. Okay, so length, breadth, and height are 30. So water is pumped from a motor. Okay, so this is the motor which pumps the water. So the efficiency of motor is 30%. Okay. So whenever you see efficiency, efficiency is nothing but output power by input power. Okay. So how much power is utilized, how much input power is utilized to produce the desired outcome. Okay. So this ratio is the efficiency. Okay. So you should remember this formula, or else it's very difficult to solve this problem. So this is called efficiency. So always remember, efficiency is nothing but output by input. Okay, how much you give and how much you get, the ratio between them is the efficiency. So this is the efficiency. So the similarity between this problem and the previous problem is in the calculation of mass of the um, water. Okay, so here we have to find the mass of the water in this tank. Okay, so we know the volume and we know the density, we can find the mass. So here are the basic values we are going to consider. So the density is we are taking the density of water as rho equal to 1000 kg per meter cube, that is 110 for 1 meter cube, and the acceleration due to gravity, g is, we are having value of 9.8 meters per second square. Okay, so these are the values we are going to consider. These are not explicitly given in the problem, so these are the values we are going to take. Okay. So first we need to calculate the mass. So this is as usual, we did it already in the previous exercise, so we can do it again. So calculation for mass of the water in a volume of 30 meter cube. Okay, so we know the volume equal to 30 meter cube. Okay, so density is mass by volume, which implies that mass equal to density times volume. So we know the density as 1000 into volume is 30. So this is the mass. So it happens to be 30,000 kg. So this is the mass of the water in a volume of 30 meter cube. Okay, so this tank now contains 30 tons or 30,000 kg of water. So let's calculate next the work done by the pump. Work done by the pump to lift this water from the ground. Lift the water. What water? 30 tons of water. 30 tons of water to a height of 40 meters. Okay, so this is the height where the tank is placed. So the work done equal to, we know it's the potential energy stored in the water. So which is mgh. So instead of m, we can put now 30,000 into G, we take it as 9.8, and H is 40 meters. Therefore, the work done is, so I have already calculated this value, and it is 11,760, and okay. So we can write it in a short form as um, this is equal to 1.176 into 10 power 7 joules. Okay, so I put a point and take the value as 10 power 7. Okay, so this is the work done by the pump. Work done by the pump. So next we have to calculate the power utilized to perform this work done. Okay, so the pump this water of 30,000 kg in what time? In 40, where in 15 minutes. Okay, so we know power equal to work done by time. So power equal to power utilized by the pump, power of the pump equal to this work done by the pump divided by the time. Okay, so what's the work done? It's 1.17 6 into 10 power 7 joules, and the time is in 15 minutes. Okay, so 15 minutes means we have to convert to seconds. Therefore 15 into 6, 60 seconds. So I have also calculated this value. So 1.176 into 10 power 7 divided by 900. So this value is 0.130666. So these are all 610. Okay, 666 into, this is 10 power 2. So if we take this, it will become 10 power 5. So we can write this as uh, 13, 13066 612. You can write this as zero point 0.6. Okay, so this is the work done, sorry, power of the pump. Okay, so much watts. Okay, power should be in watts, so don't confuse with the work done. This side unit is watts, or you can write it as watt. Okay, if you are using name, it should start with small letter, and if you are using a symbol, it should be capital letter. Okay, so now we need to find the power consumed. Okay, so the power consumed, or the input power consumed by the motor to perform this work. So this can be calculated from the efficiency. Okay. So power, electric power, okay, consumed by the pump is given by, we know from efficiency is nothing but P pump. This is the output power of the pump divided by input power, the electrical power we supplied. Okay, power input. So they are asking to calculate this value. So we can calculate power input as power of the pump divided by efficiency. Okay, eta, and we have eta equal to 30%. This eta is the 30%. So we can write this as 1366.6 divided by, for 30% you can write it as 0.3. Okay. So I have already calculated this value, and the power input is 43,555.6 watts. Okay, so you can write this as, so you can write it as 43.6 kilowatts, or 43.55 kilowatts. Kilowatts is 10 power 3 watts, so you can write it as 43.55 kilowatts. Instead of 10 power 3 we can use the kilo. So this is the input power, electrical power supplied by the electrical output to the pump to perform this work. Okay. So this is what they asked. So this is the electrical power consumed by the pump to perform this work done. So with this, let me stop this discussion. So in the next class, we can see then other problems. Okay, thank you.